With this approach, CryptDB makes the following contributions. It provides the first practical DBMS to process most SQL queries on encrypted data. This DBMS can be used to hide the database from system administrators while allowing them to perform their task, or to outsource the database on an untrusted cloud. Now, using this database with our solution for protecting the database, protecting the application against attacks, CryptDB protects the data of users logged out during an attack, even if all the servers are compromised. And this overall solution can be used to limit leakage from database applications. Now, one of our main contributions is that, in fact, CryptDB has a modest overhead. The encrypted DBMS has a throughput loss of only 26% as compared to an unencrypted plain MySQL database on TPC-C. And perhaps surprisingly, CryptDB doesn't make any changes to DBMSs and can run on existing DBMSs unchanged, such as Postgres or MySQL. So I'm going to show you how CryptDB works, and I will look at each threat one by one. In the first threat, remember that the database server was under attack, but the application is trusted, and our approach was to process SQL queries on encrypted data. For this, we introduced a lightweight proxy on the application side that is also trusted. The proxy stores the schema and the master key, but it doesn't store any data. When the application issues a query to the database server, the proxy intercepts it and transforms it by performing some encryption and rewriting, and sends it to the database server. The server processes the query on the encrypted database, returns the encrypted results to the proxy decrypts them, and sends them back to the application. So note that the proxy performs no query execution. The queries run completely at the database server. So let's see how exactly do we do SQL over encrypted data, and I will start with an example. So consider that we have the table employees at the database server. This table has 3 columns: rank, name, and salary. In fact, the database server only sees anonymized names, such as table 1, column 2, and column 3. Each gray block indicates an encrypted data item. This is what the server sees. And we use a randomized encryption scheme because these are the most secure encryption schemes. So in the salary column, we can see which are the specific ciphertexts, and on the right side, I'm showing you the actual values that are encrypted, but the server doesn't see this, just sees the encrypted data. So consider that the query comes from the application requesting all rows where salary equals 100. We can see that the server cannot do this equality directly on the encrypted data because the 2 encryptions of 100 are different because of the randomized scheme. So the server can't just do one direct equality. Instead, the first idea is to use deterministic encryption, which, as the name suggests, whenever it encrypts 100 twice, it obtains 2 equal ciphertexts. Now, all that the proxy has to do is to encrypt the value 100 with the same encryption scheme and key, and now the database server can process the equality on encrypted data as if the data was not encrypted to begin with. Now it returns the encrypted tuples to the proxy, and the proxy decrypts them and sends the results to the application. What if the application instead requested all rows with salary at least 100? We can see that the deterministic encryption does not preserve order. Even though 60 is smaller than 100, the encryption of 60 is larger than the encryption of 100. Well, it turns out that there have recently been developed order-preserving encryption schemes that preserve order. So let's try to use one of those. We can see that now the encryption of 60 is smaller than the encryption of 100. Similarly, all that the proxy has to do is to encrypt 100 with the same encryption scheme and key, and now the database server can process the order check on the encrypted data as if it was not encrypted, and returns the results to the proxy for decryption. So this example gives you insight into our 2 techniques. The first is we use a SQL-aware set of encryption schemes. And here the observation is that most SQL uses a limited set of operators. And if we can cover these operators with encryption schemes, then we can cover most SQL. The second, since different queries perform different computation on data and we need to use different encryption schemes, we adjust the encryption of the database based on the queries. So let's look at the first technique. And on this slide, I will show you the different encryption schemes we use, and I will group them in groups of roughly the same security, and the security decreases across groups. So the first is RAND, which stands for randomized encryption, which, as we've seen, is a highly secure encryption scheme that doesn't perform any functionality on the data. The second is HOM, which is roughly as secure as RAND and allows us to perform addition or multiplication on the encrypted data. Search, which was proposed by Song et al. In 2000, allows us to perform full keyword search, full word search on encrypted text, and support a restricted form of I-like. DET stands for deterministic encryption, and as we've seen, this allows us to perform equality checks on the data and support sequels such as equal, different, in, count, group by, distinct, and so forth. Join allows us to perform equality join between two columns, and since there wasn't an appropriate encryption scheme, we designed our own and proved its security, and the paper describes it in detail. Lastly, OPE stands for order preserving encryption, which, as we've seen, allows us to perform order and therefore support greater than, smaller than, sort by, order by, sort, max, min, and so forth. We used the initial protocol of Boldireva et al. From 2009. We improved the design, optimized the design, and we performed the first implementation. So I showed you 6 encryption schemes. Which one of them should we use to encrypt each data item? Well, the encryption scheme to use depends on the queries that come in, and we may not know these queries ahead of time. So one safe method may be to encrypt each column with each of these encryption schemes separately. But this will waste a lot of space and will also leak a lot of confidentiality because each column is encrypted with OPE leaking order. Instead, our idea is to stack these encryption schemes into onions. And we encrypt each data value with 3 onions because we couldn't stack all these encryption schemes in one onion. So note that the first onion encrypts the value with join, then on top of that with that, and then on top of that with RAND. And this onion is useful for equality type of operations because it has that inside. The second onion is useful for order type of operations because of OPE, and the third and the fourth are useful for search and addition. So note that within each onion, the functionality of a lower layer is strictly higher than the functionality of a higher layer. We use the same set of keys to encrypt each data item in a column, and we have a different key for different onion layers and different columns. So when we start out the database, we encrypt each item with each of these onions, and note that the outer layer of each onion is either RAND, search, or HOM, which are highly secure encryption schemes that virtually leak nothing about the data. So in this state, we leak virtually nothing about the data. But as queries come in, we need to adjust this encryption level to allow the queries to happen on the data. And this happens naturally with onions. We simply strip off layers of encryption. The proxy gives a key to the server for the specific layer of the onion by calling a user-defined function on the database server side, which is a SQL function we provide to the database server. Now, the proxy remembers what is the exposed onion level for each column. And after we stripped off a layer of the onion, we don't put it back. Therefore, future queries that perform similar operations to previous queries no longer need to strip off onion layers. So let's see how this works on an example. Again, considering our employees table. Each column becomes 3 columns. So the rank column becomes column 1 onion equality, column 1 onion order, column 1 onion search, so there's 1 column per onion type. Now each data item is encrypted with an onion. So for example, the first item in the column 1 onion equality is encrypted with the onion equality onion. Consider that a query comes at the proxy that requests all tuples where rank equals CEO. The proxy remembers that the outer layer of the first onion, the outer layer of the first column, which is the column corresponding to rank, is RAND, which means that the proxy cannot process, which means that the server cannot process the query on the encrypted data. Therefore, we need to strip off the RAND layer. And the way this works is the proxy issues an update at the database server that sets column 1 onion equality to its decryption from RAND, and does so by calling the decrypt RAND user-defined function and giving it the key for that specific layer of the onion. Now the rent layer is removed, and that is exposed. The proxy simply encrypts CEO with join and that, and now the database server can process the query on encrypted data as we saw before. So now that we saw a scene how SQL over encrypted data works, what is the resulting confidentiality level? Well, based on the queries, we expose certain encryption schemes. And each encryption scheme has a certain amount of leakage. What we guarantee because of our onion strategy is that the encryption schemes exposed for each column are the most secure encryption schemes from our encryption set that enable those queries. So for example, if we have an equality predicate on a column, then that is exposed, which leaks repeats to the server. This means that the server sees that the third item and the ninth item, for example, are equal in a column, but doesn't know what's the actual value of the item. Now, if an aggregation is performed on a column, then we expose home, from which the server doesn't learn anything. And if no comparison is performed on a column, then rand remains as the outer layer, which also doesn't leak anything. And in fact, in practice, this is quite common, as we will see in the evaluation section. But the takeaway point is that we never reveal the plaintext to the database server because we never decrypt the lowest layer of the onion. So far, we protected the database server by processing SQL on encrypted data. Let's try to make the system better by protecting against attacks to the application as well. The first thing you'll notice is that the master key can no longer live at the proxy because an attacker can get hold of it and decrypt the entire database. Therefore, we replace the master key with user keys, and each user key is naturally the user's password to the application. Each user key gives access to the user to the data he is allowed to see based on application access control. So let's see how this works at a high level. A user logs in, provides his key to the application and the proxy. Now, assuming that each user's data is separately encrypted in the database using the user's key, then the proxy can simply perform SQL over encrypted data as before. When the user is done, the proxy and the application remove the key. Now you may notice that if an attacker attacks when a user is logged in, the attacker may get hold of the user's key and therefore be able to decrypt the user's data. But the attacker has no way of getting the key of users who are logged out during an attack. And therefore, CryptDB protects the data of users who are logged out during an attack, even if all the servers are compromised. So what is challenging in such an approach? Well, so far we assume that each user's data is separate from the other users. But this doesn't work for many applications because of data sharing. And data sharing poses a few challenges that I will explain on an example together with our approach at the high level. So consider the private messages example in which only the sender and the receiver should have access to a message. And consider that we have the tables on the slide in a database. The first question is, how can we ensure cryptographically that only Alice and Bob can read a secret message? For this, what we do is we do a key chaining with which the proxy encrypts the secret message with the key corresponding to message ID 5, and then the proxy encrypts the key of message ID 5 with the password of Alice and Bob, so that it gives access to Alice and Bob to the secret message. But how can the proxy know which key chains to build? This really depends on application control policy. For this, we require the programmer to specify schema annotations. These annotations are in terms of principals for units of access control, for example, message ID 5, sender Alice, receiver Bob. The programmer specifies that each sender principal should speak for the corresponding message ID principal, meaning that should have access to that message ID. And similarly for the receiver principal. Also, the programmer specifies that each message is encrypted for the corresponding message ID principal. So we can see how logically Alice and Bob should have access to the secret message. And finally, we simply process SQL over encrypted data as before. The only difference is that instead of the proxy using one global master key, it uses a key derived from keychains. Okay. So now we saw how CryptDB works. Let me describe the implementation and evaluation. One nice feature of our implementation is that we made no change to the existing DBMSs. The reason was that whenever we wanted to change the processing of the DBMS, we used a CryptDB user-defined function. This makes CryptDB portable. Our initial implementation was in Postgres, and we ported it to MySQL with only 86 lines of code changing CryptDB. Also, our CryptDB proxy exports SQL query interface, which means that applications running in the one key case don't have to be changed to run on top of CryptDB. The applications running the multi-user key case, we saw the programmer has to provide annotations and also to change some login logout code so that the application provides the key to the proxy, as we saw in the example. In terms of our evaluation, we tried to answer 3 questions. Does CryptDB support real queries and applications? What is the resulting confidentiality? And what is the performance overhead? Before looking at real queries, let's understand what queries does CryptDB generally not support. These are more complex operators such as square root or trigonometry, or they're operations that require combining incompatible encryption schemes. For example, CryptDB does not support a plus b greater than c, because in order to compute a plus b, we would use homomorphic encryption, so the result, the summation of a and b would be encrypted with homomorphic encryption, which cannot be compared to some other value because the homomorphic encryption scheme we use does not support comparison. CryptDB could be extended to support such queries by splitting a query into multiple queries, by pre-computing columns, or by adding new encryption schemes. So now, in order to examine the real queries and applications CryptDB supports, we looked at a set of applications and traces, some of which are on this slide. PHPBB is an open source forum software. HotCRP is the conference management website for SOSP. GradApply is the MIT ECS graduate admission application. TPC-C is an industry standard benchmark for SQL. And SQL@mit.edu is a large trace of queries from a popular server at MIT. So this trace contains more than 126 million queries from many applications over more than 120,000 columns. So in the multi-user key case, we analyzed manually which were the sensitive fields and annotated them with CryptDB and protected and encrypted them with CryptDB. So note that in this case, we only encrypted the columns that were sensitive. We did not encrypt all of them. Now for TPC-C and SQL@mit.edu, we encrypted all the columns in the one key case, even if they were not sensitive, because we wanted to understand how a fully encrypted DBMS performs. The first metric we examined was the number of columns that are not supported, meaning the number of columns that have at least one query we do not support. We can see that in the case of the multi-user keys case, we support all the queries on the sensitive columns. In the case of TPC-C, we support all queries on all the columns. For the large trace, we did not support less than 1% of the queries, and these were mostly queries that had more complicated mathematical operations, such as select 1/log of a column. In terms of code change to applications, as I already said, in the one key case, there's no need to change the application. In the multi-user key case, the programmer has to specify some annotations and change some lines of code, but we can see there are not that many. To examine the resulting confidentiality of CryptDB, we looked at what was the weakest encryption scheme exposed for every column. We can see that, in fact, for most columns, the weakest encryption scheme is RAND, which is a highly secure encryption scheme. What this means is that for these columns, there was no comparison performed on them, and therefore no onion level was stripped. And this is great news because RAND doesn't leak virtually anything about the data. So this means that CryptDB doesn't leak virtually anything about most of the columns. Now, a small fraction of the columns were encrypted with OPE, which leaks order. And we manually looked at what were these fields, and we saw that they were mostly less sensitive. For example, they were the time when a post was made or the time when a private message was sent, but the actual post or the actual private message, they were encrypted with RAND. We didn't examine the large trace manually because there were too many columns. In terms of the performance overhead, this slide shows the difference in setup between an application running on top of CryptDB and an application running on top of the plain MySQL database. So we evaluated different parts of CryptDB but here I'm going to talk about the two that we consider most important. That is query latency and database server throughput. In terms of query latency, CryptDB adds 0.62 milliseconds per query on average for TPC-C. And this is mostly due to encryption and decryption of the proxy. In terms of throughput, we looked at the number of queries per second as the number of server cores increases for both MySQL and CryptDB. And we found that the throughput loss was at most 26%, which we think is a small number. To understand why this is the case, we examined the throughput in queries per second for different types of queries for MySQL and CryptDB. In fact, we can see that for most query types, the throughput loss is even less. The reason is that for these queries, the server doesn't do any cryptography in the steady state. Remember that once we peeled off a level of the onion, we no longer put it back, so queries that perform operations similar to a previous query no longer need decryption at the server. Moreover, for these queries, all that the server does is comparisons on the encrypted data the same way as it would do on unencrypted data. The only difference is that the encrypted data is a bit larger. For the second type of operations, the server has to do some cryptography, homomorphic addition, so the throughput loss is a bit higher, but still at most 50%. So overall, CryptDB is, we think, practical. So now that I showed you how CryptDB works, what is the relation to related work performing SQL over encrypted data? So fully homomorphic encryption schemes are more secure and more general. However, they are orders of magnitude less practical than CryptDB, making them prohibitive for most applications. We use some techniques from search over encrypted data to implement our I-like operation. However, these techniques alone for SQL would result in restricted SQL and inefficiency because the database server cannot build an index by itself. Systems proposals result in lower degree of security. They rewrite the DBMS internals considerably and require that the client do significant client-side filtering of the query results. Finally, CryptDB does not protect the integrity of the data, which means that if an adversary changes the data in the database, the user may receive junk data back. However, integrity attacks cannot be used in CryptDB to leak confidentiality, so the guarantee that we protect the data of logged out users still holds. In conclusion, CryptDB is the first practical DBMS for running most standard queries on encrypted data. It protects the data of users logged out during an attack, even if all the servers are compromised. And it has modest overhead and requires no changes to DBMSs. So on the website, we have the code for CryptDB, and come and see a demo of the poster session. Thank you.
Hello, Malte Schwarzkopf from Cambridge. I understand that you compute these columns as and when needed, so you peel off the layers of the onion as and when queries need them. Now, have you looked at the time dimension of this? Because if you imagine running a database for a long time, like a year, then obviously your probability of getting a query that will need the layers to be peeled off increases. So have you thought about things like maybe periodic cleanups where you discard those columns again to maintain a high level of security, or is that left to future work?
So, good question, thank you. So, for many applications, actually, the query set is fixed, meaning that the same type of queries will be issued over and over, but with different constants. For those queries, for those applications, once all the queries were issued, the levels of the onion will forever stay the same. So they will not be decreasing over time. Now, I showed you the mean level of security in our evaluation. We saw that for most applications we looked at, actually many columns were still at rand. Now, of course, there can be applications, maybe query analytics, in which the levels of the onion may continue to be peeled off because of new query types. And in that case, a technique as you propose would indeed be useful. We haven't implemented it, but would be useful.
Okay. Thank you.
In case you use per user encryption and per user keys, how do you perform the stripping of onion layers? Because it seems that in order to do the stripping, you need keys for all users, which you don't have at a time.
I see. So you're talking about the multi-user case in which you want to perform a summation over the data of multiple users.
Yes.
Right. So in that case, the data of multiple users is encrypted under different keys. So that's a good point. So there are two issues to consider here. The first is whether the data is even decryptable, and second, who performs this computation. So if the users over which we want to perform an aggregate are not logged in, then we cannot decrypt that data and we cannot perform the aggregate. And that's because we don't want someone who doesn't have access to the user's data to be able to decrypt it. Now, suppose that a user that should have access to the data is online and that user wants to perform an aggregate. Then indeed, one possibility would be, indeed the database server cannot process the aggregate directly on that data. So one possibility would be to have the proxy decrypted and perform the aggregate over the multiple keys. Or an even better possibility is for the programmer to provide more clever annotations saying that, well, this value is also encrypted for some task that performs aggregation. So then the data would also be encrypted with one key and the task can directly do the aggregation of the database server.
So I understand about aggregation, but what about stripping the onion layers? To strip the onion layers from the column, I understand, as far as I understood, you have to decrypt this column for all rows in the database, right?
Right, so in the case of the multi-user case, you only strip off the level of, for the specific users.
Okay, I see.
But also, so for the application we've been looking at, mostly the query set is well known for this kind of multi-user applications. So in fact, ahead of time, you can just start with the right onion levels to avoid
Thank
that.
you.
Okay. I think I was standing first, yeah. Brad Karp, University College London. I really like the work. I wanted to ask, in many databases, there's a lot of sharing between almost all the data in the database among many users. And so in your sort of second conclusion here, you talk about what happens when users are logged out, but I guess that means when all users are logged out because of the key chaining. Is that correct?
Right, so basically a piece of data that belongs exclusively to logged out users won't be accessible to an adversary.
But in a highly shared database, it could be that every piece of data is most of the time belonging to some logged in user. Just do you have any thoughts about what else you might do in that kind of situation?
Right, so you might have a person such as the administrator who has access to a lot of data, and when that administrator is online, indeed the attacker attacking then could get a hold of a lot of data. So one of the measures of precaution would be for a person with such high power to access data, maybe should have multiple roles. One as a normal user when he's using the database as a normal user and doesn't need to make use of that role, and sometimes, hopefully, more rarely and for a shorter period of time to use the full administrator privilege. But actually, it's part of our future work to try to reduce the amount of data of the logged in users that leaks.
Okay, I think there are also use cases where it's not just an administrator and where all the regular users share all the data. I think that case exists too, but...
Yes, so that is definitely part of our future work to try to do that.
Thank you.
Thank you.
Okay, so yes, I'll do it quickly. Paulo Verissimo from the University of Lisbon. So you use encryption schemes which selectively leak stuff, order, equality, whatever. So if I were a hacker, maybe I would try to apply a mutation of the strategy of chosen plaintext or known plaintext attacks. Let's call it chosen query or known query attack. So the question is the following. Have you studied this problem? Can you make statements about your scheme being resilient to chosen query or known query attacks?
Right, so that's a good question. So that's why when I specified the first threat, I said we're looking at the passive adversary. So we're only looking at an adversary that reads the data but doesn't take any action. So in that case, your attack wouldn't apply, and that's the kind of guarantees we offer. In the second case, in which we consider both active attacks, well, we just say we don't protect the data of users that are logged in during an attack, and the query is performed on behalf of those users. So this is all that you're saying is already included in the way we specified our guarantees.
Okay.